Hi there. Welcome to another podcast. This is Chris Clements. This one will be on LeChatelier's principle and the solubility product constant. So we'll start with LeChatelier's principle, which deals with more equilibrium concepts. So we've been through equilibrium, and you got to stick with it because we'll be on equilibrium stuff for a little more longer. So, first of all, LeChatelier's principle states that when a stress is applied to a system that is already at equilibrium, that system is going to respond in some way that will bring the system back to equilibrium. There are three types of stresses that we'll look at. Those are concentration, pressure, and temperature. I need you to recall that an equilibrium reaction is one that is a reversible reaction, that the reaction never does stop, that it is constantly making products and constantly making reactants. However, what brings it to equilibrium is that the rate of forward reaction equals the rate of reverse reaction. So do keep that in mind, please. Alrighty, the first of those stresses, as I mentioned, was concentration. We're going to look at that one. If you happen to add more reactant to a system, meaning a reaction that is already at equilibrium, then that system is going to do what it can to alleviate that stress. Again, the stress is that there is too much reactant. Well, what the system will do is use reactant to make product. And the way we speak of it in LeChatelier terms is that we will say the system will shift to the right to use the excess reactant. When you tell me what a system will do to respond to its stress, I want you to be able to address the problem at hand. And again, the problem is that there's too much reactant. So again, if we have added reactant to a system that is already at equilibrium, the reaction will shift to the right to use excess reagent. What that will in turn do is increase the product concentration. If you were to add more product, then the reaction is going to shift to the left in an effort to use the excess product. If you were to remove reactant, then you don't have enough reactant is the problem. So the reactant would shift to the left in order to replenish the lost reactant. And a fourth example of a concentration stress is if you were to remove product, then the reaction would shift to the right in order to replenish the lost product. Now we'll go over examples of each of these types of stresses, but I'm going to do an overview as I typically do for each stress first. So the second stress is pressure, and there are essentially three means of affecting pressure of gaseous systems, that is where all reactants and products are gaseous. The first of them we've actually already discussed, and that is by affecting the concentration. If we add or remove gaseous reactant or product, we can obviously affect the system's equilibrium. So I'm not going to go back over that. You can certainly review those slides if you need to. But the other two means of affecting pressure are that we can change the volume of the container in which the reaction occurs. And a third means of affecting pressure of a gaseous system is to add an inert gas. And I'll talk about each of these, the volume change and the addition of an inert gas. So if I decrease the volume of a container, think about that by, say, squeezing a balloon that's filled with a gas. That's how you can decrease the volume of a container. Then the pressure will increase. Again, think about Boyle's law, which tells us there's an indirect relationship between volume and pressure, so that if I decrease the volume, I'm going to increase the pressure. So the system is going to adjust by shifting to the side with the fewer number of moles of gaseous substance. By shifting to that side with the fewer number of moles, it will bring the pressure somewhere close to what it was at equilibrium. The idea is to get the pressure to come back down. So again, in this one, we can't state that it goes left or goes right. We simply have to look at each reaction individually, and in this particular case, if I had decreased the volume of the container, the problem would be that the pressure of the gaseous particles had increased, so the equilibrium reaction would shift to the side with the fewer number of moles of gaseous substance. If I happen to increase the volume of a container, allow it to expand in some manner, then the pressure will go down. The problem would be that the pressure is too low. So you should be able to reason that the pressure, since it's too low, needs to come up. So we will shift to the side with the greater number of moles of gaseous substance, so that the pressure can get back up to what it was at equilibrium. If you increase or decrease the volume of a container for a reaction who has equal numbers of moles of gaseous reactant and gaseous product, then the system is just going to remain stressed out, and it won't be able to reach equilibrium again. So it's a sad, sad situation, obviously, but it just can't do anything about it if it has the same number of moles on each side. Well, the third factor that I said could affect a system's equilibrium and thereby pressure was the addition of an inert gas. An inert gas is also known as a noble gas, and they are called inert because they don't tend to react with many substances. So if you add an inert gas to a system that is already at equilibrium, then there will not be a shift. The only thing that that inert gas will do is increase the total pressure of the system. The total pressure, if you recall, is the sum of all of the partial pressures. Well, adding that inert gas is just going to affect the total pressure. It's not going to change the partial pressures of the reactant gases or product gases. So again, there's no shift when you add an inert gas. The third factor that can affect a system at equilibrium is temperature. And there are essentially four scenarios that we're going to go through, because the temperature effect depends on whether the reaction is endothermic or exothermic. You need to recall that an endothermic reaction is one that absorbs heat energy, which means the energy will appear as a reactant, or if I were just writing a delta H, the delta H would have a positive value. But the better way to view this is that the energy can be treated as another reactant. If a reaction is exothermic, then it releases heat energy, so the energy can appear on the product side as just another product. If I were just writing a delta H, it would have a negative sign. So we're going to look at, in an endothermic reaction, what will happen if you add or decrease heat. That means change the temperature of it. So in an endothermic reaction where our heat is treated as a reactant, if I add more heat, then the problem is I have too much heat as reactant. So in order to reduce that amount of heat that's on the reactant side, the reaction will shift to the right to use the excess heat. Again, think of that heat as a reactant. If, however, I were to cool an endothermic reaction, that means remove heat from an endothermic reaction, it would be the same as taking away a reactant. So the problem would be that I have too little reactant, and the reaction will therefore shift to the left to replenish the missing heat. The next scenario is if I have an exothermic reaction. Again, in an exothermic reaction, pardon that telephone, I'm just going to let it ring, the heat is treated as a product, and if I were to add more heat, then it's like adding more product. If I have too much product, then the reaction will shift to the left to use the excess heat. Again, think of that heat as a product, and it will end up reducing the amount of product by making more reactant. If you remove heat, then you are going to have to treat the heat as a product again, and it's like pulling product out of it. So you would shift to the right in an effort to replenish the lost heat. So if you will, just open my PowerPoint from my website that is on colligative properties. You'll see a practice problem that has N2 gas plus 3 moles of H2 gas reacting to form 2 moles of NH3 gas and spitting out 33.3 kilojoules of energy. It's an equilibrium reaction, so it has a reversible arrow, and it is exothermic since it is producing the 33 kilojoules. And I ask that you explain the direction of shift it will experience when the following stresses are applied. A, is the system is heated. B is its container is squeezed. C is ammonia is added to the system. And D is neon is added to the system. If you want to pause the podcast at this point and think about those, that would be great. And then just start it again and we'll review A through D. So if you've paused, let's get back into it. And A, the system is heated, means that we would have too much heat as a product. So the system would shift to the left to reduce the excess heat on the product side. B, its container is squeezed, means that the volume would decrease, therefore the pressure would increase, so the reaction would shift to the side with the fewer number of moles of gas. Well, if you look at the balanced equation, there are a total of 4 moles of gas on the left side and 2 moles of gas on the right side. So in this particular case, it would shift to the right and it would produce ammonia gas. We would actually be able to note that shift because of the odor of ammonia. C is ammonia is added to the system. Well, ammonia in this particular reaction is a product. So the problem would be we have too much product. Therefore, the reaction would shift to the left in order to use the excess product. And D, neon is added to the system. Neon is an inert gas, so while it might affect the total pressure of the system at equilibrium, it will not have any effect on the partial pressures. Therefore, there will be no shift for this particular change. The second practice problem that I have on my PowerPoint asks you to consider the reaction of 2 moles of sulfur trioxide gas requiring 33.3 kilojoules in a reversible reaction to yield 2 moles of sulfur dioxide gas and 1 mole of oxygen gas. Again, explaining the direction of shift that it will experience when the following stresses are applied. A is the system is cooled. B, its container expands. C, sulfur trioxide is added to the system. And D, argon is added to the system. Again, if you wish to pause the podcast at this point to answer those and then come back to it, that would be great. So A, when the system is cooled, this particular reaction is endothermic, which means that the heat is treated as a reactant. Well, if it's cooled, it would be like taking away heat on the reactant side. So the reaction would shift to the left in order to replenish the lost heat. B, the container expands. So as the container expands, its volume increases, which means its pressure decreases. So it would shift to the side with a greater number of particles. In this particular case, there are 2 moles of gas on the left side and 3 moles of gas on the right side. So in this particular case, again, you have to look at each case. The reaction would shift to the right side in order to bring the pressure back up. C tells us sulfur trioxide is added to the system. Well, sulfur trioxide happens to be a reactant. So if I were to add more reactant, the problem would be an excess of reactant. So I would shift to the right to reduce the excess reactant amount. And D, surprise, surprise, argon is added to the system. Argon is another inert gas. So again, there will be no change in the system. It will not shift left, nor will it shift right, because only the total pressure is affected, not the partial pressure of the reacting or produced gases. Okay, well, that's going to conclude the stuff on LeChatelier's principle. But because all of this that we're doing of late relates to equilibrium, I decided that I would put a solubility product constant podcast together with LeChatelier and do the same thing with the PowerPoint. So if you did open up that PowerPoint, the next slide after the second LeChatelier practice problem is the beginning of solubility product constant, which means we're going to apply equilibrium concepts to salts. You might recall that a salt is simply an ionic compound, but not all salts will dissolve in water. We know, for example, that sodium chloride dissolves in water, but not all salts are completely soluble in water. Well, the solubility product constant which is represented by an uppercase K, again like an equilibrium constant, but with a subscript of lowercase sp for solubility product, is going to tell us the level to which a salt dissolves in a particular solvent, that being water. So the KSP tells us the level to which a salt dissolves, and it's expressed as a K value was expressed. Only gaseous and aqueous substances are represented in K expressions, you must recall. In a salt dissociation, the only substances that are aqueous are the products. The reactant is always going to be a solid, and that reactant is always our salt. So I want you to consider the salt silver hydroxide, and I want you to write its formula. If you're looking at the PowerPoint at this point, you just put it in slideshow mode and keep hitting your down or right arrow and it will advance through it. So the formula for silver hydroxide should be AgOH. Silver has a 1 positive charge, hydroxide ion has a 1 negative charge. When you do your little crisscrossing, you end up with AgOH. I now want you to write its dissociation into its ions as we put it in water. You can write water as a catalyst if you want over the yield sign to show that it is present, but it's not changing. Water is still water, whether at the beginning of the reaction or at the end of the reaction is what that means. So if I write the dissociation, I'm going to write AgOH and put in parentheses S to indicate its solid phase. And then with a reversible arrow, write what it dissociates to yield. So it dissociates to yield 1 silver, 1 positive ion that is aqueous, since it's floating around in water, and 1 hydroxide ion, which is OH, 1 negative, and is also aqueous, since it's floating around in water. Again, I have 1 of each of those ions, and the reason that I have 1 of each of those ions is because of the formula AgOH. We'll get more practice on this in just a bit. I want you to make sure that you pay attention to your phases. And as you look at your phases, I want you to think about writing a K expression. However, this time it's going to be called a KSP expression. Recall that you put products raised to the power of their coefficients in your numerator, and reactants raised to the power of their coefficients in your denominator. And again, the only phases that you can include are aqueous and gaseous substances. So your KSP expression should equal KSP equals the concentration of Ag 1 positive raised to the first times the concentration of OH 1 negative raised to the first. They are not over anything. If you want to put that they're over something, put that they're over 1. The AgOH is not present because it's a solid. And the reason the Ag1 positive and the OH1 negative both have 1s as their powers is because only 1 mole of each ion was yielded. This KSP expression is going to allow you to work 3 types of problems. One is where you determine the concentrations of ions that have dissolved in water. A second type is to determine the solubility of the salt. It's always going to equal X in your equilibrium chart, by the way. And yes, we will keep doing equilibrium charts. And a third is to determine the KSP of a salt. Meaning you can work backwards to find the actual equilibrium constant, just as you did with equilibrium problems. So we're just going to jump into our practice problems. The first one, again, if you're looking at my PowerPoint, tells you to determine the concentration of each ion if the KSP of calcium fluoride is 4.0 times 10 to the negative 11. You don't tend to have units represented with KSP. For some reason, chemistry folks just don't get into putting their units. Alrighty, so the first step is to write the dissociation of the salt. And in this case, we have calcium fluoride. Write your formula for calcium fluoride. Once you have that written, you should have CaF2. It's going to be a solid that will dissociate in water to yield Ca2 positive ion that is aqueous and F1 negative ion that is aqueous. Now think about what the formula CaF2 tells you about your number of moles of calcium ion and your number of moles of fluoride ion. It tells us that every time we have 1 mole of CaF2 dissociate in water, we will get 1 mole of calcium ion and 2 moles of fluoride ion. It's reflecting the mole to mole to mole ratio. The mole to mole ratio for the calcium to fluoride ion is therefore 1 to 2. You're going to use this throughout the problem so you make sure that that formula of your salt is correct. Step 2 is to make a dissociation chart, just like you did for the other equilibrium reactions. But again, we can only use gaseous and aqueous substances. So if you want to make your 3 column headings CaF2, Ca2 positive, and F1 negative and put brackets around them to indicate molarities, that's fine. But what I want you to realize is that your initial concentration of CaF2 cannot exist. It's nothing. It's not that it's 0, it's just not present. So we don't fill anything in the CaF2 column. And that means that you will have an initial concentration of Ca2 positive and F1 negative that is 0. If you recall, the next line for an equilibrium chart is your change line. That change line must reflect your mole-to-mole ratio, and it must use variables. So since we had 0 calcium ion initially and 0 fluoride ion initially, we're going to get plus 1x for calcium's change and plus 2x for fluoride's change. Again, the mole-to-mole ratio is reflected, and we use variables, which means that at equilibrium we will have x for calcium ion and 2x for fluoride ion. Step 3 is to write your KSP expression and then plug in what you have at equilibrium. So your KSP expression reads KSP equals the concentration of calcium ion raised to the first power times the concentration of fluoride ion raised to the second power. Again, your mole-to-mole ratio tells you what your powers will be. So it's kind of like a check and balance system where you have your mole-to-mole ratio reflected all over the place. Once you plug in what you know to that KSP expression, you should have 4.0 times 10 to the negative 11 equals the concentration of x raised to the first power times the concentration of 2x raised to the second power. Well, if you consolidate what's on the right side there, you're going to have 4x cubed on the right side. Then solve for x, and you should find that x is 2.15 times 10 to the negative 4th. The next step is to use your value for x and the equilibrium line of your chart to figure out what I actually asked you to find, which was the concentrations of the ions. So go back to that equilibrium chart, and the equilibrium concentration of calcium ion is x, so it is 2.15 times 10 to the negative 4th molar. The equilibrium concentration of fluoride ion was 2x, so multiply 2 by 2.15 times 10 to the negative 4th, and you'll find it's 4.3 times 10 to the negative 4th molar. You can do a check, just like you did for equilibrium reactions with this, and prove to yourself that you get the KSP if you wish to. The next problem is the second type of problem, which is to determine the solubility of calcium fluoride from your work that you did in problem 1. Step 1, you've actually already done. In fact, you've done all the work for this problem, but I'm going to explain it to you. The mole-to-mole-to-mole ratio for the salt to turn into its ions is 1 to 1 to 2 in this particular case. The solubility of the salt is equal to the concentration of the calcium ion is what that means. What you can just keep in mind is that the solubility of the salt is always going to equal x in your equilibrium line of your chart, meaning 1x, because you're always going to have 1 mole of your salt itself. So the answer to this problem is that the solubility of the salt is 2.15 times 10 to the negative 4th molar, which means for every liter of solution you have, you may dissolve 2.15 times 10 to the negative fourth moles of calcium fluoride. If you exceed that number of moles of calcium fluoride, then you're going to end up having a solution that exceeds its saturation point, which means some of the calcium fluoride will precipitate or fall out of solution. Problem 3 is to determine the value of the solubility of a product constant, meaning find a KSP of a salt. So in this case, I want you to determine the value of the solubility product constant of bismuth sulfide, whose solubility is 1 times 10 to the negative 15th molar. Again, I want you to recognize that the solubility, that key word, solubility, will always equal X in a KSP problem. So your first step is to write the dissociation of the salt and then write your KSP expression. So I picked a weird one, bismuth sulfide. Bismuth has a charge of 3 positive and sulfide has a charge of 2 negative. Place it in water is the idea here. So you're taking solid bismuth sulfide and putting it in water, where water can be written above your yield sign, or you don't have to write it at all. It's understood. And your formula for bismuth sulfide should be Bi2S3. It will dissociate to yield 2 moles of bismuth ion that are aqueous and 3 moles of sulfide ion that are aqueous. Therefore, your KSP expression will read KSP equals the concentration of bismuth ion to the 2nd power times the concentration of sulfide ion to the 3rd power. So once you plug in what you know, if you want to set up an equilibrium chart, you can do so. You will find that you don't have any bismuth or sulfide ion initially, and that your change in concentration for bismuth ion is plus 2x. Your change for concentration of sulfide ion is plus 3x. At equilibrium, you'll have 2x for bismuth ion and 3x for sulfide ion. And if we plug into the KSP expression what we know, we will end up realizing we were given x. So you'll have 2 times x quantity squared and 3 times x quantity cubed. If you want to consolidate that a little bit, you can realize that 2x quantity squared times 3x quantity cubed is 108x to the 5th. So now if I plug in my solubility, which you recall is x, then I am going to have, I'm going to use my consolidated form, 108 times 1.0 times 10 to the negative 15th to the 5th power. Now remember your order of operations. You are going to end up with a KSP value that is 1.08 times 10 to the negative 73rd molar. Well, what that exceedingly small number tells us is that bismuth sulfide really doesn't like to dissolve in water. Think about that. 1.08 times 10 to the negative 73rd moles of bismuth sulfide will dissolve in every 1 liter of water. That's a very, very tiny number of moles. What we can do with that is determine how many grams of bismuth sulfide that would be. So that's your next step, is to convert moles of bismuth sulfide to grams of bismuth sulfide. Figure out how many grams of bismuth sulfide can dissolve in a liter of water. I'll leave you with that. Have fun with it. And again, go to my site and check out the practice sheets, or stay on this podcast site and check out the practice sheets. Have a good day. Bye.